if we want to just look at another example of fast equilibrium, the first thing that we're going to look at is, you've got to see this. Okay, it says fast reversible. That's going to be a clue that you may need to do this. Not necessarily. Sometimes they throw it in there and it just is a distractor. But I know that this is my slow step. It tells me what is the rate, what rate law is derived from this mechanism. Well, I'm going to start with the slow step. Rate is equal to K times H times CO. That's my slow step. So this is my rate determining step. But why can't I keep it like this? Because it has an intermediate. We can't include the intermediate in it. Okay? So I can automatically know I'm going to do a substitution right here. But this one's going to be a little bit trickier because it's a 2-to-1 ratio here. So I have this, but then I say, okay, so this is for step 2. Okay? And then we can call that the rate determining step. Okay? But for step 1, now I'm going to skip over where I write rate forward equals rate reverse, and I'm just going to go straight to the rate. I can say that K forward times H2 is equal to K reversed times H to what? To the second power. Because in an elementary step, the coefficients become the exponents. Alright? So, I have to isolate the A, so K forward over K reversed is equal to H squared, but I need to substitute that in for H. So what do I have to do? Sorry, I left off something. H2 is equal to H squared. So what do I have to do? I got to take the square root of it, right? I got to take it to the 1/2. So it's going to be K forward, K reversed, H2 to the 1/2 is equal to H. So then I substitute into the rate law, and you end up getting rate is equal to K times K forward, K reversed. Now, technically, you're taking the square root of both sides. It would be the square root of KF, KR, but it's still going to be constant, and a constant times a constant. The square root of a constant is still a constant. Okay, so you don't have to worry about any of that. But times H2 to the 1/2 is equal to K prime times H2 to the 1/2. So this one, number 1, shows how we have to do the substitution. Number 2, you can have a fractional exponent. Now, I'm going to have you work in a little bit year 2009. That's the only time in all of my teaching AP that they came out with a fractional exponent on, and that's in your packet. I'm going to let you work on that in just a bit. Okay? So, when you have this, you have to work through and show the proof. We can pretty much see what's going to happen, but you have to show the proof. This is the proof that you have to say. Okay? Now, 2009 had a half. It had this type of thing in it. Okay? So in so I said, oh man, whatever. So I started teaching this. I probably didn't teach it up until 2009 because I'd never seen it on the AP test since 1991. Okay, so I taught it all through the year 2018. But then that never showed up again. We were short on time, so I skipped over it. 2019 showed back up on the test. The 1 year I didn't teach it showed back up on the test, and I'll show you that problem here in a second. Okay? So So we just have to know this. The odds of it being on the test are slim, but you have to know how to do this proof. Okay? It is 1 every 10 years, what I'm kind of seeing, but you know, it's whoever's writing the test, what do they feel like? All right. So let's look at 2019. Oh, I just got to do this. And you can, oh, not that. You can look this up on College Board and find this problem. Okay? So the first thing that we look at here is we look at my 3 graphs. Now, I know it's small, but this is natural log of concentration, 1 over concentration, and just concentration. Okay? Which one is the most linear? The one in the middle, right? 1 over concentration. What does that mean about my order of the reaction? It's second order. Okay? So that's just going through here, looking at the graph. It's going to be second order. So as we go through and look at, I had to make it small so you can see all 3 graphs. I'll make it bigger now when we're doing the problems. Okay, so explain how the graph indicates the reaction is second order. And your explanation is simply going to be?
The 1 over concentration.
The graph of 1 over concentration versus time is linear. Okay, so then the rate law, what's the rate law going to be? What did we just say? What's the order? Okay, so so the rate is equal to K times NO2 squared. Easy enough. I sure wish I could manipulate my computer from up there. I used to be able to when I had an iPad. Now I don't have that. Okay. Consider 2 possible mechanisms. This is 2019. Okay? Is the rate law described by mechanism 1 shown to be consistent? Well, what are the 2 things that we have to show in order for it to be consistent?
They add up and
Do they add up?
they
Okay.
save.
So NO3 cancels out. And that's it, right? So we get 2 NO2s going to 2 NO plus O2. And that's the same as the overall rate law, overall equation. Then, what's my rate law going to be?
KNO squared, or KNO2.
NO2 squared, right? Which is the same as the experimentally determined rate law that we just did. Okay? So yes, is the rate law described by mechanisms consistent with the rate law you wrote in part B? Yes. Why? Because the rate law of the slow step, the rate determining step, is the same as the experimentally determined rate law. Okay? But then we go, is the rate law described by mechanism 2 below consistent with the rate law you wrote? Okay? So now we have the fast equilibrium.
Yes.
Okay? Now, in your brain, you can automatically make a substitution for what?
The N2O4.
The N2O4 is going to be substituted, the 2 NO2s are going to substitute in for that. So you can know right off the bat, yes. Does everybody kind of see how that substitution would work? If this is like an equal sign, then we know that we can substitute this in for that. Okay, so this is going to be my rate law. But you got to go through the proof. You just can't say yes. In your justify your answer, you got to show some work, and you just can't say this can be substituted into there. Because you got to explain the why can it be substituted. Because rate forward equals rate reverse. Okay? So they're picky on the answer. Okay? I was a reader. I didn't read this question, but I was a reader this year when on this test out in Utah. And I talked to a lot of people that were grading this, and we talked all about what the grading rubric was supposed to be, and you had to have some kind of work, some kind of proof of this, okay? So we would say, for step 2, the rate is equal to K times what? N2O4. But in step 1, what can we say?
K forward NO2 squared equals K reverse
Times
N2O4.
N2O4. Then it's just math. K forward over K reversed, NO2 squared is equal to N2O4 concentration. Substituting into the rate law, you say rate is equal to K times K forward, K reversed, NO2 squared. Okay, so you do that, but then it says justify your answer, so then you have to again say yes, it's valid because the rate law of the slow step is the same as the experimentally determined rate law. And the equations, okay, but they just ask about the rate law, they don't ask about the mechanism itself, so you only have to explain the rate law part. But if it asks for is it a valid mechanism, you would have to say the second criteria of yes, the equations add up to the overall equation, and the rate law, the slow step is the same as the experimentally determined rate law. Okay? That's all there is. So we need to be able to know the mechanism. So, were there any catalysts in this one? No. What's the NO3 called?
Intermediate.
Okay, is there an intermediate in this one?
Yeah.
N2O4. Okay, so everybody understands and can identify the intermediate. Okay. Get out the packet, and I want you to do 2009, but just part D and E. Okay, so hopefully you had time to just kind of go through and do the proof. But is CH3Cl a catalyst or is it an intermediate? It's an intermediate because again, it's not an initial, it's not going to be a reactant, it's formed and then consumed in the middle. Okay? Identify the order with respect to each one. So now this is again, in order to get the order, you have to do the substitution. Now what do we see that, just by inspection, because again, Cl going to 2Cl, what do you think the order is going to be with respect to Cl2? Nobody?
CL square.
It's going to be squared
Or
for the Cl2.
it's just CL.
Well, it's 1 here and it's 2 there. This is my slow step. Okay?
Oh,
It's
yeah.
going to be raised to the 1/2.
Yeah.
So I'm going to say for step 2, rate is equal to K times CH4 times Cl, just Cl. But for step 1, the rate forward, K forward times Cl2 is equal to K reversed times Cl squared. So Kf over Kr times Cl2 is equal to Cl squared. So Kf over Kr times Cl2 to the 1/2 is equal to the Cl. Substituting that in, and I'm going to skip the 1 step, rate is going to equal some new constant prime times CH4 times Cl2 to the 1/2. So what's the order with respect to CH4? First order. What's the order with respect to Cl2? 1/2. The overall order is going to be 1/2.
Oh, I did. I guess I did it wrong.
Okay? That's year, what's that, 2009? So 2009, 2019. Those were the only 2 years that I've seen this fast equilibrium on there. Okay? Now, let's just review. Does anybody have any questions on that part of it? Okay? You understand the whole concept of a mechanism, of an elementary step, that the coefficients become the exponents. You can differentiate between intermediate and catalyst. Okay? And so, this is just a little caveat to the problems again that shows up. As far as all of the other stuff, order of the reaction and doing all that, that shows up all the time, every test. It's just whether or not you have to do the substitution or not is the key. Now, if it was multiple choice question, you can just do the mental multiple, you don't have to show work or anything, you can just kind of do it, by intuition and answer your question of whether it's a valid mechanism or not. Okay? So, let's look at this one. And it's going to be way down at the bottom. But the rate constant for the first order decomposition of cyclobutane is 9.2 times 10 to the minus third time per seconds. Here's the reaction. How long will it take for 80% of the sample of C4H8 to decompose? I want you to go see, first off, it's time. Okay? Second off, in purple it says integrated rate law. So which rate law do you think we should use? And since it's first order, now notice how they kind of, and they can say if it's AT over this, but I would use the one that's on the equation sheet, which says that the natural log of the concentration of A at any time t is equal to negative KT. Is it plus or minus? Plus the natural log of A initially. Right? And so that's your integrated. Now again, they're just, you know that when you subtract, you divide, they're just doing the math, and then they inverted these and got rid of the negative sign. But this is the form that you're gonna have on your AP test. Okay, so go ahead and see if you can do this. For those of you working right now, let me give you just a little hint. How do I calculate the concentration at time t? If 80% is consumed, decomposed, how much is going to be left at time t? 20%. Okay? 20% is what we're going to put here, not 80. But you don't put 20 either. You put 20% of your initial concentration. But we don't know what the initial concentration is, do we? Okay, so how would we do that then? Do what?
Just one molar.
Well, or we don't know what it is, so we can just use. Or we just use X. The X's will cancel out. Right? So if you go natural log of X, pardon me, 0.2X is equal to negative, they give you the value of K, which is 9.2 times 10 to the minus third, plus the natural log of X. So when you bring that over, it's going to be the natural log of 0.2 times X all over X, right? Yeah. Do what? Now, you could have done what Advite did, is just put, if you put 1 molar in there, it's gonna come out to the same thing. You know, you just pick an initial concentration, and the concentrations are gonna cancel out right here when you do that. So what does T equal? So 125 seconds? 74? 0.9 something? So it's 175 seconds? Did anybody get that on their own before I explained it? Okay? So again, when you have that, you can just kind of make up amount if they don't give it to you. Okay? So let's just say, what's the half-life going to be of this reaction?
You just changed that to 0.5 salt.
Okay? What's the natural log of 0.5 going to be? Does anybody remember that, what that equation is? T1/2 is equal to 0.693. Now, 0.693 is the natural log of 0.5. Okay, because we just put, because you put 0.5x over x, so it's always going to be the natural log of 0.5.
Is it negative?
Yeah.
0.6?
Yeah, so it'd be the negative natural log.
Now, this is good.
Because there's a.
It's got to be the negative of that, you mean?
Yeah, and then,
Yeah.
Yeah, I guess because the way we bring it over here, because it's negative KT, so you're dividing by negative K,
yeah.
okay?
Nine.
No, no, it just turns out to equal that,
Yeah.
okay? When you substitute thing, the negative gets, because of that negative, it gets rid of the, for the time, it gets rid of the negative. All right, so we need to be able to know half-life. What is the definition of half-life?
How long it takes for 50% decompose.
To react, 50% to react, okay? So, you need to be able to know what are the 2 factors for an effective collision. What are they? What 2 things have to happen for it to be an effective collision? They have to have enough energy to overcome energy of activation. Okay, now I'm sure on this video that all you heard was wah, 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 wah. So what she said was, number 1, they have to collide with enough energy to overcome EA. And then number 2, that you have to have, collide with the proper orientation to where you have the reactant bonds begin to break and product bonds begin to form. So we have those 2 criteria, so you need to know those. Then there are 4 factors that affect the rate of the reaction. What are the 4 factors?
Temperature.
Temperature, okay, let's stop right there. how does temperature increase the rate of the reaction?
More molecules have enough energy to overpower activation energy.
Okay, and the higher the temperature, and we want to use the Maxwell-Boltzmann temperature distribution graph to show how T2 has greater number of molecules overcoming EA than T1. Okay, you need to be able to do that. What else does temperature do?
Increases the number of collisions.
Increases the number of collisions because the molecules are moving faster. So if there's more collisions, you increase the probability of having proper orientation where reactive bonds begin to break and product bonds begin to form. Okay, so what's the second factor? Somebody else.
Rush.
Not pressure, but it's related to pressure. Well, if you change either one of those, you're changing the concentration. Okay? And how does increasing the concentration generally increase the rate? What does increasing concentration do?
Higher probability of collision.
Okay, well, more collisions, so higher probability of
Orientation.
proper orientation to where reactant bonds begin to break and product bonds begin to form. What's the third one? Really? Can we say two words? Surface area, very good. Okay, increasing the surface area. What does increasing surface area do?
Collision.
Increases.
Okay, it allows more collisions to occur per second at any given amount of time, which then increases the probability of having proper orientation where reactant bonds begin to break and product bonds begin to form. And the fourth one? Well, I just heard mumbles.
Another hand.
Okay, what's the fourth one?
That's the
Begins with a C.
cattle.
A catalyst.
Oh, yeah, that's pretty good.
Okay, and what does a catalyst do?
Speed it up.
How?
It decreases activation energy.
Okay, it decreases the activation energy, which to allow, so more molecules at any given temperature will have enough energy to overcome EA. Okay? Now, you should be able to explain that one both with the Maxwell-Boltzmann temperature distribution graph showing EA moving to the left, or with your energy diagram to where it shows the lower activation energy. You need to be able to know both of those graphs, forwards and backwards. Potential energy, the energy diagram, which is reactants with activation energy going to products, as well as the Maxwell-Boltzmann temperature distribution graph. Okay?
Alright.
Then you need to be able to calculate rate law, both from the differential, experimental data that we've done the most of, be able to find the value of K, including the constants, and then find the rate at any given, and also find the relative rate, so if we know the rate of disappearance of one, what would be the rate of appearance of another one. You need to be able to do integrated rate law, which is going to be the relationship between time. We just showed the graph. I think most of y'all are pretty good with recognizing the graph. But looking at the y-axis, that if it's concentration versus time, it's zero order. If it's linear with natural log of concentration versus time, that's first order. And if it's linear with 1 over concentration versus time, it's second order. Okay, then we need to be able to say, should be able to say, okay, given an initial concentration, how long will it take for the concentration to decrease to this? Or if the reaction proceeds for this many minutes, what's the concentration going to be of the thing at the end? Anytime there's time involved, we're going to want to use the integrated rate law. Then lastly, you need to understand about reaction mechanisms. You need to be able to identify intermediates and catalysts. You need to be able to write a rate law for the rate determining step using the coefficients as your exponents. You need to know the two criteria that what makes a mechanism valid. What are the two criteria to make a mechanism valid?
Add up to the final equation.
They have to all add up to the final overall equation, and
Rate determining step has same rate law as the
the experimentally determined rate law. Okay? And then lastly, you need to be able to do this proof. Not this proof, but proof that we've been doing, that proof. Okay? So that proof. The one we just worked on today. Tomorrow is just a review day for you. I'm gonna look at Princeton Review right now and just kind of look and see how much there is. But the Princeton Review will be your review for tomorrow. Test on Thursday, lab due on Friday. And again, on the labs, you already have almost all the way through 5 as far as the calculations. So number 6 is just a question, and it says compare your K's to the class values. Well, we don't have class data, so just compare your K to the other K's, just within your own data. You know, just make a comment about the precision of your values. In other words, is K really constant based upon your data? And I think most of y'all got pretty close to the same answers for K all the way through. So if you got the same value for K, what does that mean about your precision? Good or bad?
Good.
It's good. Okay? And we don't really want to say pretty good, you know. You want to explain, you know, just kind of saying words, you know, this one was a little off, but, you know, overall with experimental, because are you getting the meniscus right there? Sometimes on the time, you guys were a little slow on the fingers for when it changed, okay? Some people had trouble pouring the actual, from the graduated cylinder, making it all get into the beaker. That wasn't in here. Oh, did that happen with y'all? No. Okay, because it happened in 7th period, and so, anyway. So those are all different things that could affect your value of K. All right, well, happy studying, and we will welcome back on Thursday everybody together. I know you're excited about that. Woohoo! All right, go.